Hello, everybody. Thank you for attending today's webinar on evaluating ionizer performance. Let's see. I'm Jim McKeon, National Sales Manager for the Desco brand. Also participating today will be Will De La Isla, who's the Desco Industries Corporate Sales Manager for Latin America, and Jeffrey Brake, who is the Desco Brand Manager. Jeffrey will be organizing the questions. We'll have you have the opportunity to ask questions as we go along. Please pull down the toolbox and you can ask them there. And we'll have a break halfway through for questions, and also we'll answer questions at the end of the presentation. A general overview of today's webinar will be discussing meters that are used for evaluating ionizer performance, basics of offset voltage and decay rate, and what is the optimal placement of ionizers. There are two general categories of meters that can be used for evaluating and testing ionizer performance. One is the field meter ionization test kit setup, in which basically a field meter with attachments can be used to test the ionizer, and also the more formal laboratory type charge plate monitor product. The field meter system, a field meter is basically measures surface voltage and polarity, generally up to 20,000 volts. To test ionizers, you need to also have an isolated conductive plate, which collects the ions, and a charging unit, so that you charge the ionization test kit positively, and then it tells you how fast the negative ions are neutralizing from 1,000 volts to 100, and then vice versa. This type of a unit can be used for compliance verification only, not for qualification, and not for any other types of tests. The charge plate monitor is more of a laboratory type product. It features a 6x6 inch measuring plate, which is called out by the ESD standard S20.20 on ionization. It has an embedded timer for measuring the decay rate, and it also shows peak voltages. This can be used for compliance verification and product qualification and calibration as well. So there are two ways to measure the performance of an ionizer: offset voltage and discharge time. Offset voltage measures the balance of ions created by the ionizer. This is a test that's required by S20.20, and the maximum limit per S20.20 is 30 plus 35 or minus 35 volts. Discharge time is the rate at which a charge must be neutralized to eliminate a static problem. The normal test range is how fast a charge is decayed from 1,000 volts to 100 volts. So Will is going to perform a few demos on using the two types of instrumentation and the two test methods. Will?
Hey, thank you, Jim. I appreciate it. Again, my name is Will De La Isla. Thank you for joining us today. As Jim said, we're going to go over these two types of systems of monitoring your ionizers in your work environment. The first one being your static field meter, as I will forward it on, the static field meter with the isolated hood. Now, a lot of people have always asked, I know Jim has done many, a lot of people come up and they want to monitor the ionizers just with the static field meter. It will pick it up. It'll be a little bit not as specific to the ions that are generated, because it has a, if you could see, measuring LED lighting that has to be. So what the isolated plate does is gives you the specific distance and gives you a better average of the ions that are collected. So what we're going to do is we're going to use this hood, place this on, and And with this, you're going to be able to put this in the airstream, measure the offset voltage, which what I'm doing, I'm setting this up at 12 inches. Hopefully you can see the display there. I also have the charge plate monitor, and you can see the float voltage is less, basically at 0. So this balance is well within. You can see both of them are pretty exact. So you can use both of these measurement tools to audit your ionization. Now, this one thing is measuring balance performance. So the ESD requirement is plus or minus 35 volts. So either 35 volts positive, 35 volts negative, and understanding that ions, we're probably producing about 7 kV positive and negative, but in a balanced mixed ion output from the ionizer. So what you're seeing here is basically 0 volts producing both. So what happens, and I know Jim has seen this a lot of times ionizers have been running for a year, and it may show a very good balance like it shows here. You may think, look, the balance is great, but how does it perform? Now, how do we test performance? Now, using a charger device like this produces both positive and negative voltage of 1,000 volts, or a little bit over 1,000 volts. So the industry standard says, how quick can we reduce a charge of 1,000 volts down to 100? So using this method of the field meter, we need to time it with your stopwatch or some sort of stopwatch or your phone to kind of make sure that it's neutralizing the charge very rapidly. So what I'm going to do right now is put a positive charge on the plate over 1,000. You can see, remove it, and you can see how fast that neutralized. Okay, so then the other part is I'll put a negative charge now over 1,300, and you can see about 3 seconds, 2 to 3 seconds. Obviously, this meter is not going to show as quick of a reduction compared to a charge plate monitor, which has a capacity, has its own built-in timer and such. Okay, so this is one way of auditing at the work environment. You don't need to bring out this whole equipment. The charge plate monitor, if you're going to do float and decay, it's more of an laboratory. And with the charge plate monitor, if you're going to make any adjustments, you want to do it with the charge plate monitor in a laboratory area to 12 inches. Like we have this set up for 12 inches. Right now, the charge plate monitor is measuring 2 feet from this distance. And let's just see what we find out here. At 2 feet, right now we did the 12-inch with the auditing tool using the charger. Everything seemed to work out fine. The balance is perfect. At 1 foot, let's see what happens here. So we're going to charge this. As you can see on the display, over 1,000 volts. I let it go. You can see the timer. It has a built-in timer, so no need to have a stopwatch or anything to mount it. You can see what happens. I will put it on positive. We'll do the same. So we'll illustrate. Oops, we didn't do the. So here goes the timer. So pretty much the same, about 5 or 6 seconds. And this is with some of this being blocked in the airstream. And we'll talk about that a little bit more about obstruction and later in our conversation. But having obstructions and still have the isolated plate, at 2 feet, we're still having a pretty good neutralization. So understanding what we're doing is offset or balance is the mixture of ions that you're producing through the ionizer. That's one example of what you have to test for your ionization using your ionization test kit is balance. Make sure that it's not producing a charge that's isolated on your circuit board. The second step is performance, and that's what using the charge plate again. Charging the device and making sure that it's removing the charge both positive and negative. So those are examples using both the ion test kit that we have and a charge plate monitor doing balance, offset, and performance, which we call decay test for both positive and negative. So back to you, Jim. I think if you have any questions so far on balance and decay, let me know. We could take it from here, Jim or Jeffrey. We have any questions?
We do have a question about ionization. The question, I think we talked about insulators and ionization, but does ionization work with conductors as well? Or
Absolutely.
can you talk about that a little bit?
Absolutely. Well, here's a couple examples. We always use plastic blades and a conductive, right? And if you actually see what's on our isolated plate is a metal conductor, and we're actually charging that conductor, and that's just like as we could have charged this metal plate, which could be a kit. We could charge this up. Actually, it's better to charge an isolated plate, which is a conductor, to 1400 volts, which does remove the charge. Same would happen with any conductor or any part. So yes, it would. Its job is to ionize any conductor, isolated conductor, insulated plastics, whatever it has. It'll attract the opposite polarity to that charge and neutralize it. So very good question.
Thank you. We have another question. I think we talked about this in a previous webinar, but we're using DC ionization. Can you talk a little bit about the difference between AC and DC?
Yeah, AC ionization is using one power source that has alternating current. So what it does is produces positive, negative through one emitter pin, a focus, or multiple emitter pins, but it's creating alternating current, positive and negative, in a 60 hertz cycle. There's different ACs that have 60 hertz or high frequency hertz, which just produce it a lot faster, a lot more ions come out. DC is more controllable, which you can monitor with circuitry, feedback systems, and you can actually offset the balance, positive and negative. AC is really strictly designed on spacing of the emitter pins and certain distances, and there's no adjustment, there's no clean indicators. With DC, you have positive and negative alternating, so an equal amount of positive emitter pins and negative emitter pins in a balanced state. And using circuitry feedback systems, you could set up alarms if you find that it drifts off to one area or not. So there's a lot of benefits, and for both, AC is mainly used in more areas where industrial, where you just want to produce a high volume of ions and where you're separating materials, and you really don't care too much about offsets. It's more about safety hazards of maybe shock hazards, which a lot of people have done in the film industry. But DC is mainly used for critical type areas where you could have some feedback, some adjustments, some control. So
okay, thanks, Will. Can you do the charge plate monitor test at 12 inches? Somebody asked to see that test.
Absolutely. Remove this. So here we go. Still the balance, like we said, it's still pretty well. I'm going to do the negative first, over 1,000 volts. 1.3 seconds. We will move it to negative, charge it up. 1.7 seconds. So.
Okay. And 12 inches is required for calibrating benchtop style ionizers. Is that right?
Yeah. Yes. Benchtops is 12 inches is the requirement. Overhead ionizers are usually 18 inches above the work environment, and several test points. And you can see those on in the ESD guidelines 3.1. But this would be how you would measure no obstruction. We have it even on low fan speed. So and it's still performing well under what you should have. So this is a great ionizer, DC steady state. You can see the balance. So this is the way you would test a benchtop ionizer in a lab condition.
Gotcha. Okay, that's it for questions right now. Jim, do you want to continue?
Sure. So we're going to talk about how far away do ionizers need to be from the target being the area where an insulator and a static sensor device come together. So we just discussed the fact that when you're calibrating an ionizer, A bench top is 12 inches away and a overhead might be 18 inches away. And that's to give it a comparative distance to a manufacturer specification. But what we're going to talk about here is how far away do the ionizers need to be and how fast do they have to work to solve the problem that they're trying to address. And the common problem is an insulator induces a charge onto the static sensitive device, which makes that device then subject to possible charge device events. So how far away do ionizers need to be from the target? There are 3 parts of that process to evaluate that and come up with that answer. First, you have to measure the charge on the insulator that's in question. In the picture here, we're saying that this buzzer has approximately 3,000 volts on it. The second is, what is the amount of time the device is exposed to the insulator before a conductive material could touch the device, creating a charge device model event. So we're going to use 8 seconds for the test that Will's going to do in a few minutes. We're talking about 8 seconds, a device being next to the insulator for 8 seconds before the device might be touched. And then a key part of this is, how long does it take for the ionizer to take the charge off the insulator before a conductive material could touch the device? So basically we're saying that the ionizer needs to take the charge off the insulator in less than 8 seconds in order to take the charge off to prevent the charge device model event. So some tips for ionizer placement: point it directly at the target area where insulator and the ESD susceptible device would be in close proximity. Use gravity to your advantage. Sometimes overhead ionizers will cover more area and provide some advantage in that way. And consider mounting options. Use an arm for benchtop ionizer, tilt the overhead, but you need to make sure that the stream of ions is attacking the place of the target area and decaying an amount of time to prevent problems. So common mistakes made in ionizer placement. This is a cluttered workbench. You can see the ionizer at the back of the bench, and you've got some frames there and some other pieces of equipment. So you want to make sure that you measure how long it's taking that ionizer to decay the charge on any insulators that are in that area, and then calculate the time that it needs to happen in. Too far away. We often get this with overhead ionizers. Companies like to put ionizers up higher because it's less airflow on the person and it might be easier to set them up. But I'm going to guess that ionizer being 4 or 5 feet above, it's going to probably be decaying 1,000 volts to 100 at that bench level, maybe 15, 20 seconds. And if the insulator and the device combine or come into the same area and the device gets touched in less than 15 seconds, then you're not really solving the problem, leaving open the possibility of some defects. Poor maintenance of ionizers. Sometimes people have a great ionizer program and they set it up properly, but they neglect maintenance. So this is a picture. You can see a lot of dust on the cage of this ionizer, and we can't see it, but I'm sure that there are that the emitter pins are covered with the same kind of material, and that prevents efficient and the proper amount of ions from being produced. It's a little bit like a spark plug that's all gummed up. If it doesn't work properly, it doesn't do its job. So proper maintenance, cleaning of ionizers on some kind of a regular basis is important. So Will is going to demonstrate some of the equipment in specific applications. And again, we're using the sort of the 8-second required static decay for these demonstrations. Will?
Hey, thanks, Jim. And like Jim said, there's no standard for performance and decay. It's you will have to set up your own. And like Jim said, we're going to set up 8 seconds as our focal point for what we want to manage as a performance structure. Okay. But first, before we do that is Jim talked about having plastics and around your components, right? Now we're going to talk a little bit about induction first. Why do we need ionization? And this is kind of a reason I want to do this demo so you guys can understand how static is induced onto your critical components. And what I'm going to use, I'm going to illustrate an insulated material, which could be very similar like your plastic buttons that are on your circuit board, a conductive plate, which would be basically like your actual components on this product. So what I'm going to do is, you'll see this, is that I'll charge up this plastic over 1,000 volts. I will ground out this component. So now there's no charge on this plate. I could put it near the product using no ionization. I have everything turned off. There's no ionization. With a rule of thumb, as I'm talking 3, 4, 5 seconds without touching it, now I've just induced over 300 volts on this product. Now, if I ground it, then you're going to have the same problem or an ESD event. Now, I took the charge off by grounding it to the mat. I put it again near the component, not using any ionization. What happens? We induce a charge again continuously. So without ionization, you're not removing that static charge. That is the main focal point for an ESD event. Without a charge, without static, there's no event, right? So our job is to reduce the static from happening. So now I'm going to do the same demo, having our ionizer on and using our 8-second or threshold that we have done. Now, when I charge up the plastic, put in the airstream, ground out the plate, put it near the component or my process. Now, and I 3, 4, 5 seconds. Now, when I go to check it, it's less than the 50 volt. So let's do that again, because now we're being protected by the coverage. Your 800 product, we have close to 0 on the thing. I'm going to put it right down near my process. As I'm working, now I'm going to check. There's no charge anymore. So this is a great example of how an ionizer could really benefit your area by reducing the static charge as it's being created in the work environment. Okay, so that is, first of all, I wanted to show that. So now it basically removed the charge in a couple seconds, right? Because we had it focused. Now let's see what happens. Again, this is our product. We're going to do how does distance affect performance. We're going to start talking about that. Now I have my product at 12 inches. I'm going to do our decay test at 12 inches. So again, to kind of redo the test, 2.6 seconds, well within our structure of 8 seconds, right? So now I have this tape measure here. So I'm going to move this back to 2 feet. Let's see what happens at 2 feet. So here we have 2 feet. Not sure if you could see it, but this is marked for 2 feet. We would do the same test. So let's see what happens to our performance. 6 seconds. So we're at 6 seconds. So if I was to be working on my product at this distance, I still fall within the 8 second that we're saying we need ionization. I could still feel the air everything's still working, our performance is still up, I will check it at positive just so you guys can see the difference between both. Negative ions are usually more mobile, they get out quicker, so it's always a little bit less, as you saw. I put a positive decay, the negative ions seem to attract a lot quicker, so you can see in the performance. Now I'm going to move it a little bit further. I'm going to use, I have my ionizer, I'm working on product, or this is where I have determined I'm going to have my circuit boards, or is it protected or not at 8 seconds, right? So now I'll try my negative decay time, and let's see what the timer tells us. So look, it's above. So if you could see 10 seconds. So now we have determined that 3 feet is not going to meet our 8-second standard that we have issued for performance, right? So let's try positive. Let's see what happens at positive. So we've already failed the negative side. Now we're going to test the positive just to ensure that both polarities are being defined. So see, we're just at the outside of that. So we can now determine that 3 feet is not an acceptable for performance. Balance is okay, but we're not removing that charge fast enough to protect our circuit board from any ESD events from happening. It's not going to cover it the way we have established an 8-second test procedure, okay? So now, what would be another form of setting up? Say I have to have the meter here. Now we have other applications, other things that we could use. What would be a good one, Jim? What can we do? Now we have a wide area.
Well, you could move the ionizer closer to the target. You could use an arm maybe to put it right above the target, or you stated that we're going to we need to leave the work on the devices to the far right side of the bench. But if that wasn't necessary, you could move the target products closer to the ionizer. So it looks like no matter what, it's got to be within 2 feet.
Yeah, and there's another thing, we could use an overhead. This is where some people ask, well, I need to cover more of a work environment because I have parts isolated all over the bench, right? So let's do this. This is a 2-fan ionizer. Instead of using a bench top, we have a 2-fan ionizer here. And will it cover a wider area? Now, this is a good test for you, those of you watching. Now I have a 2-fan ionizer going on, trying to cover the area. I have it tilted here. Now let's do the test. Will it meet the 8-second that we've established for performance? So look at that. This one just met it at this distance. This could be another application where we could use for performing. Would be an overhead or moving in. Let's try another thing. Let's try this overhead. Just met it at 3 feet. I could feel the airflow here. The balance is still very good, so it meets it. Another application would be, like Jim had said, we have articulating arms. We could build, what if I move this in? And I wanted to cover not only this area, but the full area. So let's see what happens by just changing our application a little bit. This would be another alternative. Let's see what this is able to do. Let's move this out. Will it cover both? So let's charge this up and let's see what this does. So there you go, 5.9 seconds. So this could be another application you could use. Instead of having the bench top blowing across, you could have it blowing down, keeping it off the work environment and still cover this area if needed. An overhead could be another step, maybe making a 3-fan overhead to cover all the test points around the bench. This is another good application for that. So this would be an application of how you would generate something like that. Now, any questions so far? And then I'll go over obstructions. Another key component into where people may have an ionizer in their work environment, but they have obstructions that they're not thinking that it's going to cause any problems. Any questions at this point, Jeffrey?
We have a question about using ionizers in clean rooms. Is there any special requirements for that?
Clean rooms, you need to have ionizers. A lot of times these are painted or powder coated, so there's not a lot of slough, but particulation is a big issue in clean rooms. We generally have some stainless steel ionizations that are easy to clean. There's no particulate to be used or that could get it generated onto the product. There's some room ionization that could be used for clean rooms. Usually ESA problems are more generally the cause of problems in clean rooms because they're using a lot of medical plastics. So ESA, which is electrostatic attraction, so any contaminations kind of bond onto the product. So you have to remove that with ionization and remove the static or the bonding of it so it doesn't attract and it flows on the floor and it gets sucked up through the vacuum. So, but
Can I
for
add
particulation,
something, Will?
the problem. Sure, go ahead, Jimmy.
I think also worth noting is that when you're trying to protect static sensitive devices from charge device model event, speed is more important. So you've got to get the charge off the insulator so it doesn't get induced onto the device. But in a clean room type applications, I'd say a better percentage of the time, the reason for having ionizers is to for, as Will said, for electrostatic attraction issues. So it doesn't really have to work as fast. And if you have constant air going over an area, then it's not going to attract the dust. The other thing is we try to get the insulators and the charges down to less than 100, but in a particulate type environment, you might not need to get all the way down to 100 to prevent that object, that material, from attracting dust from the air. So it's a little bit different.
Right, exactly. But good question. Anything else, Jeffrey?
Let's do the obstruction demo right now, and then there are a few questions that I want to do right after that.
Okay, so the common problems that we find in applications where the assembler, has all this equipment, everything's working properly, but now they have to bring in some maybe test equipment to test the circuit. So something like this, most commonly some type of fluid measurement to test your circuit board whether actually inspecting it. Well, what happens here is what happens to your performance now, and we're going to test that. So if I do a performance test, having an obstruction in front of my ionizer because I'm thinking my ionizer is working, it's not alarming, but now we're obstructing the airflow. Airflow is one of the most common problems with testing ionization, is that everything could be working, but a lot of times your work environment, if you have different things, will cause problems for that. So that's another thing you need to look at is look at the area. Do you need certain things in the area that are going to obstruct the air? By obstructing the air, you're going to obstruct the performance of your ionizers. This is a common thing that you may find. Or another thing that is typical that you'll find is that a simple, maybe the carrying packages that you have the circuit boards in, they may be open because they took the product away from the work environment and they put it and they're now testing it. Now they have it in front of the ionizer, and it's gonna degrade the performance of the ionizer. A lot of users seem to like heaters because in the winter their hands get cold. What happens to ionizers? I know Jim has seen this all over the place, maybe in Canada and other places we've traveled all over the world, is we end up finding people that use heaters, they put them under their desk because they want to warm up their feet. So heaters sometimes is not something that we recommend because operators will use them as other forms instead of blowing them at the actual product that you're trying to protect. They'll blow them to maybe keep their hands warm or their feet warm or put them under their work environment. It's not helping your application or your product. So these are things that are going to affect, as you see, 14 seconds. You need the airflow to move the ions and to remove the static charge from the product. So is there any other demos you wanted to see? Is that, and this is another, we could do the same illustration, say the application of the arm. Maybe if we absolutely need this carrying case there, then we could bring in our arm that's made to cover above, and you could adjust it however you want to. You could still have the things that you need on your work environment, but now I could charge this up and we'll see what kind of performance we have. And like you see, 1.6 seconds. And just by changing your application, you could see we're using the same ionizer as you saw, just moving it up and covering the area that's needed. So using these type of tools or an overhead ionizer, you could cover more area, keep it off the work environment where you have meters and equipment that you absolutely need to have on your production floor. You could have different alternatives to maintain the performance level that you need on your work environment. Anything else, Jeffrey?
We had a question or somebody asked to show the balance again. Can you do a demo of that? I know we did it at the beginning, but somebody asked,
with the charge plate?
Can you do it one more time? Either with the charge plate or, yeah, just go through balance one more time.
Okay, so balance is the performance of both positive and negative coming from the fan. So if we have our plate, our charge plate monitor, and you can see our balance at the plate right now is 0 volts. If I obstruct it or change it, or if I charge up a plate near it, it may change the offset. But if you can see the balance here where I need it, where my product is being built, is, if you can see the display, it's 0 basically. So which it means that you have the same amount of positive ions as you do negative. And that's what you want, because if this offset is off, you could be putting 35, 40 volts, 50 volts of charge on your isolated circuit. So by maintaining a 0 volt, that's as good as you can get it. So this is the offset, or what you would call the balance of the mixture of ions that we're producing from this ionizer and maintaining. So we have a steady state sensing system that will sense the output of the ions coming out. So our feedback system is maintaining a 0 volts at this work environment. And let's see, I could even participate. No problem.
Jim, are you still there? Shoot, there, Jim,
Okay.
You there?
Yes, I'd like to just say can I say one more thing about the offset voltage?
Sure.
Yes.
Absolutely.
So there's 2 ways you can do it. You can do it like Will just did, where he just zeroed the charge plate and blew the ionizer off it, or you can combine it with your decay test. So when you do your decay test, wherever the test ends, that will show you what the balance is. So you can sort of do, take 2 readings with with 1 test.
Well, like this one, now I have them both on. It's still the float on the meter here. You could have it on float or decay and balance. And right now our balance is 0. Decay is, I could run a decay and you'll see what the end result will be. By the time it settles in, it'll be back to 0. And you can see it. So balance, it removes all the static from that.
There you go.
Perfect.
Hey, Will, I have a question for you. This
Yes,
is
sir.
a little bit of an ingest question. So you did the test where you put the plate to the far right and then tested it with the overhead?
Yeah.
Right, and we snuck in under 8 seconds. Did you practice that before you did it, or you just kind of, because we didn't do it we didn't do that test in our practices, or were you just kind of figuring it would work?
I just, what we do all the time, we need to just test it in the field. I have used these type of ionizers all around. For this type of workbench, I would probably use a three fan, but I was just illustrating what a 2 fan could also do.
Right.
And just adding 1 more extra fan from what we're adding on a bench top, you could see a 2 fan could cover a pretty wide area.
Right.
So
Okay.
this is
That was good.
definitely a great style, a good selection for your work environment.
Hey,
Any other
guys, we have
questions?
another question. We have another question. Jim, can you review the 125 volt rule at 1 inch?
Okay. So S20.20 before the 2014 revision had a rule that any charged insulator greater than 2000 volts had to be at least 12 inches away from the device. And I used to think so, so if it's 1,999, it's okay, which didn't make sense. And I think other people were asking the same question. So now the rule is anything between 125 volts and 1,999 volts needs to be at least an inch away. So if you have a less than 125 volts based on S20.20 requirements, you can put it as close as you want to the device.
Gotcha. Thank you. A couple questions. I can answer this one, but the people are asking a couple different questions about either raising about temperatures in the work area and relative humidity in the work area, and if that can be used instead of ionization. The simple answer to that is no. You can't get the relative humidity high enough to be significant in reducing charges off insulators, at least at the production level that we deal with. So there, I will also mention there's a couple articles referenced on the DESCO blog about relative humidity in electronics production area and it's out of control. So if people want to go to the DESCO blog and pull up those articles, just search for relative humidity and you'll be able to reference those articles. One other question, Will, can you comment about ozone and ionization?
Yeah, ozone is a byproduct of creating ions. So that's typically all DCs fell well within the ozone requirement of 0.02. And mostly AC usually creates a lot more ozone. Usually the 60 hertz ionizers will be very borderline to it, but it's the things you have to look at are the high frequency ionization create a lot more ions, so in thus creates more ozone. And those are safety regulations that that OSHA and other companies are testing for. Our ionizer, our DC ionizer, are fell way within the safety guidelines. So 0.02 feet per minute is one of the tests that they do. So ours do fall within that. So that is something that someone should look at. If there's operators working in that general area, OSHA does test for ozone. So that is an ozone test. There is a requirement for that.
Yeah, and I would add that, I mean, we've tested our ionizers. We've had multiple customers test our ionizers, but if your facility needs to test them for safety requirements, we're happy to provide a demo unit for you guys for a facility to determine that, or your safety coordinator to determine the safety of ionizers. So I think that's all the questions we have now. Jim, do you have a few more slides?
Yes. I'd also, if I could, Jeffrey, just like to add a little bit more about humidity. In S20.20, humidity isn't mentioned at all. And in TR20.20, which is a more detailed ESD standard, there's a couple of paragraphs on it, but really it only references, I think they suggest between 30 and 70 for comfort and for solderability issues. I've always felt that there's not much said about it because the ESD Association doesn't ever want anybody thinking they don't need a static control program because they have high humidity. I'll also say that there are some major military aerospace type manufacturers that require of themselves and of their subcontractors that when the humidity gets below 30% in the building, they're required to use ionization. So some of these companies, some of these subcontractors, you know, to describe it lightly, they have ionizers sitting in their desks, and then when it gets down to 30, they pull them out and set them up. So that's really the only major type of humidity ionizer requirement type of event that I know of. Let's see.
Thank you, Jim.
So you're welcome. So we've talked today about ionizers and instruments used that can be used to test them. If you're interested in evaluating any of the items that we discussed today, your local DESCO sales rep will be able to lend you equipment for time to evaluate those for evaluation. All the reps have a field kit, an ionization test kit, and most of them have a couple of different ionizers. We also offer a demo program where you have, usually it's 30 or 60 days to evaluate a demo, which you get brand new out of our facility. And at that time, you can either buy it or send it back. And we're extending that to 120-day terms. And that can be done with DESCO, or that can be done with a DESCO distributor. So if you're interested in either of those, you could contact me in the US and Will for anyone from Mexico, and we can let you know how that gets done. And I think that's about it. Thanks to everybody for coming today. And if you have any questions, please feel free to ask. Jeffrey?
Yeah,
Thank you, Jim. Thank you, Will. Thank you, everybody, for joining us today. Appreciate it.
all right.
If there's any other questions, feel free to contact us. Bye-bye.